Okay. All right. So rate law. So today, if you look this up online, you're going to see there's lots of strange ways you're going to see this shown and the ability to calculate at a rate law. And I'm going to show you what I think is the easiest way. But before that, as I said, I would go over the answers to this first thing. So let me go over the answers to this. So it says the graph and table below show how the volume of carbon dioxide collected varied against time. So collecting carbon dioxide, concentration versus time. When both small and large calcium carbonate chips were added to an excess amount of hydrochloric acid in two separate experiments. So you can see the volume of the small chips compared to the volume of the large chips. All right, and there's the graph. So this is the opposite of what I showed you yesterday. Yesterday I showed you, let me just draw on it, I don't know, I'll erase it. But I showed you starting up here at some concentration and then decreasing down to zero. You can see this time we're doing the opposite. We're actually starting with zero. So how does that work? Well, we're not looking at reactants, we're looking at products. So instead of decreasing reactants, we have an increasing product. What can be deduced about the total mass of the chips relative to one another used in each of the two experiments? Explain. Well, notice how they gave the same amount of product. So they both ended up at, what are we measuring? We're measuring, remember, volume of carbon dioxide in milliliters, and they both produced 80 milliliters eventually. So I would say they would be the same because you got the same amount of product. How long did each experiment take to go completion, and how can you tell from the data? Well, if we go all the way back up to the data, you can see it went 79, 80, and that took 135 seconds. So the first one took 135 seconds, but it took 165 seconds for the larger chips to get to 80. So 135 seconds and 165 seconds. And the way you can tell is when it got to the final volume, 80. What are the possible units of rate of reaction in these experiments? Well, they're not measuring concentration. So we don't want to say molarity versus time, and the time is seconds. We want to say volume in milliliters. So it's the volume in milliliters versus seconds. Volume in milliliters. Write the chemical reaction for this process. So we have, I'll do it down at the bottom here, a little more room. So we're adding calcium carbonate chips to hydrochloric acid. Double replacement reaction, you get calcium with chloride, right? Positive, negative. And then you get hydrogen with carbonate, which gives you H2CO3, which if you remember gives you H2O and CO2. So there's the gas that's produced. Now it's already, no, it's not balanced. So we need a 2 there. That gives us 2 of those. And now we're balanced. So the 2, and now we're balanced. Yeah, so it's a 1-to-2 ratio over there. Why is the gas produced at different rates in the two different experiments? Well, this is one of the 5 ways to increase the rate of a chemical reaction, which is increase the surface area. So the smaller chips are going to, remember, the same mass. So question 1, we have the same mass. So smaller chips are going to react faster. Smaller chips will react faster. Explain how the apparatus listed below could be used to generate the data in the table. An Erlenmeyer flask, normally we would have done this lab already, which is part of the problem, although I'm not sure. Did you guys do the bark test last year? We may have done the bark test, but we collected it a little differently. So the Erlenmeyer flask, so that's the one, remember, that has the smaller top than a bottom. So what you do is, how are we doing it? So we have Erlenmeyer, we have a delivery tube and some tubing. We have a quick syringe, and we have a balance, a graduated cylinder. I mean, there's a bunch of different ways you could do this. The way that I generally would do it is I would fill this, well, we have a syringe, so we don't even need that. So I would actually just use the graduated cylinder probably. I would put a stopper on it. I would use the tube. I guess you could use the Erlenmeyer flask too. So the rubber tubing connected to the syringe. So hook the tube of the syringe in, and then you'd have the plunger inside of here. So the plunger inside of here as the gas. So we make sure all of the air is out of this. And then as the gas is produced, the plunger will, get pushed out the back, equal to the volume of CO2 collected. So that would be how I would do that. So push the syringe all the way in, hook it to the tube right here, start the reaction, the gas is going to bubble, and then it will collect in the tube. Explain how the experiment could be modified to investigate the role of temperature and or concentration. All right, well, temperature is easy. Use the same size chips, only the big or only the small, and just do it at 2 different temperature HCl. Increase the HCl up to 50 degrees Celsius and 100 degrees Celsius, or 10, 20, 30, 40, and 50, however you want to design that. And then same thing with the concentration. So rather than starting with the same amount of each of the two, again, don't change surface area. We don't want to change two things. So make maybe the large chips this time and add 10 grams, 20 grams, 30 grams, 40 grams, 50 grams. And that will change the concentration. Okay, so where are we headed today? So today, as I said, we're going to learn something called an empirical rate law, or just referred to as a rate law. The general format of a rate law is rate equals K, and this K is called the rate constant. So we have K as the rate constant. And then we have the rate again, how fast. Usually in molarity per second, but it could be any really concentration per time. And then you only ever have reactants. So different than a rate expression, these are never negative. I mean, they're never negative because we're saying we're just looking for the rate of change, how fast it's occurring. So they're never negative. They're always positive, and we never include products, only reactants. So only reactants. All right, notice also that this is an exponent of 2, but there's no 2 in the balanced chemical reaction. So those coefficients that became fractions before have really nothing whatsoever to do with the exponents that we're going to find in these reactions. So that is the rate of the chemical reaction is proportional to the square of the concentration of NO2. The proportionality constant, also known as the rate constant, and we would say this reaction is second order with respect to NO2. Now, CO is not in the rate law, which means it's probably 0 order, but we'll get to that. Don't worry so much about that. And then you could add them together and get the overall rate, but there's only one there. Rate laws will always have the same format. It'll be equal to the rate constant times the concentration of the reactants raised to their powers. So how do we do it? I don't think an explanation of it is as good as just trying it. So on the next page, and remember, brackets means molarity, always. Brackets always means molarity, and we're talking initial rate. So this is the rate right at the exact beginning of the reaction. If we know the rate at the beginning of the reaction, what we can find is if we know the rate at the beginning, we find the constant, and then we can calculate it anywhere along the curve without knowing any calculus. That's really the great thing about this. All right, so let's start by writing the rate law. So rate equals K. I always do it the same way. I just put both reactants in there. And then you can call them X and Y, or A and B, or smiley face, sad face, whatever it is you want to solve. We're going to solve for them individually anyway, so it doesn't really matter what you call them. All right, now here's how I like to do this. I do this by using the phrase, by what factor is this changing? So by what factor is the concentration changing? And then by what factor does that affect the rate? And let me show you, and I think it'll make the most sense, as I already said twice. All right, so to do A, so let's say we want to find A. So to do A, we want B to remain constant. So we want B, not equals, but we want B to not change. So what I mean by that is I'm going to pick these first 2 experiments to compare by what factor are they changing. All right, so I can see that B is not changing. So by what factor is B changing? By what factor? Well, the factor B would changing there would be by 1. It's not changing. That's by factor 1. You're multiplying by 1. You're just raising it to the first power. You're multiplying by 1 is really what you're trying to say there. If you can't figure out the factor, so by what factor? Just divide them. So do, run, let's say they're 2 over run 1 in this case. So 1 divided by 1. All right, so how is A changing now? A is going from, and I made these easy, I made them 1s and 2s in the beginning. So A is going from a molarity of 1 to a molarity of 2. By what factor is that? It is doubling. It's changing by a factor of 2. Once again, if you can't figure it out, divide 2 divided by 1. Again, easy there. So what we want to say now is 2 raised to what power? Because remember, these are exponents we're talking about. We don't care about b because b is not changing. So raising the factor of 1 to any exponent whatsoever is still 1. So by b staying the same, even if it affects the rate, it's not going to affect the rate comparing the first 2 experiments because, again, it's not changing. But a is double. What happened to the rate? Well, the rate went from 2, again, the rate, I didn't put the rates in there. We're going to say molarity per second for all of them. It's going from 4 to 2. It's also doubling. So now we have to solve that algebraic equation right there. Now I say that algebraic equation because what you're really doing is solving a logarithmic function. You just don't realize you are. I'll show you that tomorrow. We should be able to do the logs in our head. So 2 to what exponent gives me a 2? It's obviously a 1. If it was 2 to what exponent gives you a 4? And it would be squared. 2 to what exponent gives you an 8? That would be cubed. That's as far as you go, generally. All right, so now we have a. So a's exponent is 1. So now I can come back up here to my rate law, and I now know that the exponent on a is a 1. And you don't have to write 1s, just like algebra class, but it doesn't hurt to put it in. You can put it there. What we say that is it is first order with respect to a. All right, well, what about b? All right, so which 2 do I want to do b? Let me change the color just to let us know we're doing b. Notice in the first and the third experiment, a is not changing. So again, we don't want a to change. B changes though. B doubles. And the rate goes from 2 to 4. And so the rate also doubles. So 2 to what power gives us a 2 once again. B is also first order with respect to b. So it is second order overall. Overall, you just add them together. So first order with respect to a, first order with respect to b, second order overall. All right, what about calculating k? So now that we wrote the rate law, rate equals k times a to the first, b to the first. And you could write those 1s or not. So now just pick a line, doesn't matter which line you pick, and solve for k. Now, they always ask another question in conjunction with calculate k, and that is, what are the units on k? The units on k. All right, so we have to do both. So let's plug in the rate. So 2 molarity per second equals k times a, 1.0. Don't forget to raise it to the first, 1.0. Don't forget to raise it to the first, although again, easy enough there. So 1 to the first, 1 to the first. So our answer is k equals 2. Now, what are the units? Scroll up, give myself a little space. Actually, I'll just do it over here. All right, so the units. We have the rate, which is molarity per second. And then we have k, which is what we're trying to find. And then it's molarity times molarity. So you get molarity per second equals molarity squared. Divide both sides by molarity squared. So see, the molarity on the top cancels with one of the molarities on the bottom, and you get 1 over molarity seconds. Going back to what I wrote yesterday, you'll see this oftentimes written as molarity to the -1, seconds to the -1, or you'll see it as moles per liter for molarity, so liters to the -1, seconds to the -1. Very often done that way. All right, let's try the next one. So as I said, in the beginning, I kept it easy, but I did highlight each of the things that you need to watch for. All right, so rate equals k. I'm going to write it over here, then I'll just fill it in. So rate equals k times a to what power, b to what power. So let me do a first. So to do a, I'm going to do 1 and 2 again, and a is doubling. And the rate this time is not doubling, but going 4 times. By what factor is it changing? By a factor of 4. So so 2 to what power is 4? A is squared. So now we know the exponent. It's second order with respect to a. So second order. When I do b, once again, I'm going to choose 2 trials where a is not changing now. So the first and the third one, b is doubling. 2 to what power equals, and the rate is going from 2 to 4, also doubling. So once again, we now have the order. So it's first order with respect to b, and third order overall. So again, you just add the exponents. What about k? Plug them in. So the rate is 4k times 1 squared times 2 to the first. You can see this time I chose the last of them. Doesn't matter which one you pick, you'll get the same answer. So once again, it comes out to be 2. This time the units are 1 over molarity squared seconds. A shortcut to this, it's third order overall, which means I have molarity of the third. It's always molarity per second. So you can see what's going to happen every time is whatever the overall reaction is, the exponent on the bottom of k's unit is going to be 1 less than that. So if it's third order overall, you're going to have squared. If it's second order overall, you're going to have to the first. And if it's first order overall, then you're going to have to the 0, or it won't be there. Which brings us to this one. So rate equals k times a times b. Let's do a. I'm going to do the first 2 again. You can see I made these easy in the beginning. 2 to what power? So not 3 to what power? Remember, by what factor? So 6.0 divided by 3.0, if you can't figure out the factor, equals 1 to 4. And so a, again, is to the second power. When we do b, so b is doubling, going from 1 to the third one. A rate is going 8 times. There's that one I said. That's cubed. This is 5th order overall. Add the 2 together. So since it's 5th order overall, 1 over molarity to the 4th seconds. Now you just subtract 1 over molarity. It's the molarity on the top. I didn't do the number there. You could plug it in. All right, so not A's and B's, but an actual data. So you can see this time there are 3 reactants. So we have to do all 3. So rate equals K times BrO3 minus times Br minus times H plus. So now we're going to do each one individually. I'll start with, I like to do them actually right above it. You'll see as we start to do more of these. I'm going to compare that one right there, and I'm going to see that it doubles. So 2, I'm going in that direction. So 0.05 to 0.1. And if you're unsure, 0.01 divided by 0.005. And that will get it to you. And so we now see these done not changing, and the rate molarity per unit time. So we'll say molarity per second also doubles, and so first. So you'll see that's how I actually solve these. And then I'll leave some space off to the side if I need some room to write. When I do the next one, I can pick these 2. Not changing. Once again, doubles. 2 to what power equals? It goes from 20 to 40, also doubles. Br is also to the first power. And now the third one, I'm going to pick the last 2. And you can see that that's doubling. 2 to what power equals? It's going from 40 to 160. That's 4 times as much. And so that's squared. Now, as I said, you could come up with a number. Just pick a row and plug it in. It doesn't matter which row you pick. You're going to get the same answer. And if you're not sure of that, try it. You'll see that you will convince yourself that you get the same answer. But the units for K, so it's first order, second order, 4th order overall. The fact that it's 4th order overall means 1 over molarity of 3rd seconds. All right, so try example 5, 6, and 7. Hit pause. I'm going to do the answers right now. And then I want you to try page 8 for homework. Try those. They're mostly rate laws. There's a couple of questions related to what we did yesterday in terms of increasing the rate of the reaction. So once again, hit pause. And if you don't want to calculate K in each of them, you can just do the units, but do the units. All right, so here are the answers. All right, first one. So rate equals K times, this time we have NO2 and we have CO. I'm going to go with, I'll do this one first. So this one's going from, now notice it's times 10 to the minus 3, which would be 15 times 10 to the minus 4. So you could see it. And again, if you don't see that, divide them, because that one's probably hard to see. So then I'm going to get my calculator out. I only shared my, you're not going to see my calculator. 2.5 times 10 to the minus 8 divided by 2.8 times 10 to the minus 9. Because like I said, sometimes the by what factor is not as obvious. Now it says 8.92. So, these are experimental data, and they will sometimes throw that at you, meaning, do you recognize that that's a 9, 8.92? So 3 to what power equals 9 squared. So NO2 is second order with respect to NO2. Second order. When we do CO, so now I don't want this, so I'm going to do the first two. You can see that is doubling. So 2 to what power equals, and it's staying the same by a factor of 1. Anything to the 0 power is 1. Meaning we don't even have to write CO in our rate law because it's not going to affect the overall rate of the reaction. You can change the concentration of CO, but it doesn't make the reaction go any faster. That's what that means. It's 0 order, meaning it does not affect the overall rate or how fast the reaction is occurring. All right, so now as for K then, as I said, you could plug one of them in. We're only going to plug that in and square it. There's the rate, but the units for K are going to be 1 over molarity seconds. How do I know? Well, it's second order overall, and so you take away one of the M's. Next one. This says, find the order of the reaction with respect to the reactant, the overall order of the rate law, and the value of the rate constant in the units. As I said, I'm not going to do the overall. You can do that. I do want you to do, though, the units. This time we have the per minute, though, notice. And there's that minus 1. So molarity per minute or molarity minus 1. First two works. That's doubling. 2 to what power equals. That's 4 times. And so x is squared. So rate equals K times x squared. Y, I'll do those two. And again, if you can't tell what's happening there, notice it's going in this direction, it's going down. So it's actually half, but you can look at it going in that direction. You don't have to look at it going down. What I mean by that, if you look at it going from this direction to that direction, it doubles. And we're gonna look at it going in that direction then, but notice it stayed the same. So like the last one, Y is 0 order, and so we don't have to include it. Now, with this time, we do have to calculate K because we need to know what the rate is in the fourth one. So just pick one. So I'm just going to pick the first one times 0.05 squared. 1 divided by 0.005 squared. And we get 40,000 units. 1 over molarity seconds, right? Second order, so you end up with 1 molarity on the bottom. Now we know what K is, so to calculate the rate of that one, so rate equals, we just plug in K, 1 over molarity seconds, or minutes, sorry, minutes, times 0.0750 squared. And you get 225. Oh, that might not be right, actually. Let me check the syntax of my calculator. 0.075. 40,000. Oh, that's right. Yep, 225. And the units would be molarity per minute. Molarity per minute. And the last one. All right. So what about this one? Molarity per second this time. So we're doing the same thing. I'm going to do the first two doubling. 2 to what power equals. That doubles. So it's first rate equals K times A to the first. B. It's like if I pick those two again. Now, once again, I don't want to look at it. I mean, you could look at it as going down and saying it's going 0.5 to what power gives you 0.5, which works if it's a first, but are you going to recognize a squared? So why not go in that direction and saying it's doubling? So 2 to what power equals, we're going in that direction and it doubles. And you can see that it's easy. So it's A to the first, B to the first, second overall, 1 over molarity seconds. And you can plug the rest in. I think you'll find that to be easy enough. All right. So tomorrow we continue with it. Let me know if you have any questions.